Hi and welcome to today's maths class. Today we're going to be looking at differentiating rational powers. So just a quick reminder of what we mean by that. When I have a rational power, that means the power, that's this power here, is in a fractional form. Okay, so if I've got y equals x to the power of 1 on n, where n is an integer, although not 0, then that means this is a rational number, 1 on n. Bearing in mind that when my function is in this form, x must be greater than 0, because if my n value is even, for example, if this is x to the power of a half, that's the square root of x, which we can't have a negative value for x there. So the rule then is actually the same as the rule that you've been learning all this time. dy dx is going to be, this here is the power from up here. I bring the power out the front and then I subtract 1 from the power. So the rule really isn't different at all. So what I'm going to do is I'm going to first take you through an example of differentiating by first principles, and then I'm going to go through some worked examples looking at this rule. So let's start with first principles. I'm going to differentiate f of x equals the square root of x. Of course, if I want to differentiate by first principles, I need my rule f dash of x equals the limit as h approaches 0 of f of x plus h minus f of x over h. All right, so what I'm going to do is I'm going to substitute in f of x plus h and f of x and leave h, obviously. Limit as h approaches 0. So f of x plus h will be this with x replaced by x plus h. So it's the square root of x plus h minus f of x, which is just this, root x, all over h. Okay. My next step is a little bit of a trick, and what I'm going to do is I'm going to use the difference of two squares pattern. Remember, a minus b times a plus b gives me a squared minus b squared. So if these terms in the brackets are square rooted, when I square them later, I get just the whole number. I get this a and this b. So if I follow this pattern here, I'm going to multiply my numerator by square root of x plus h plus the square root of x, and now I have formed this pattern of two square roots minus and plus in the two brackets. Of course, if I do that and I don't want to change the value, then I have to do the same thing on the denominator, and so that's what I've done there. So when I expand that out, I expect to get a minus b. That is this part of underneath the square root sign minus this underneath the square root sign. And once I do it, you'll see why it's a trick and why it helps me out. So I take my numerator, I get x plus h, that's this part, minus x, that's this part. That is the expansion of these two brackets here. Then on my denominator, I've still got this h, and now I've got the square root of x plus h plus the square root of x. Now in a moment you'll see why this trick works. The problem that I had at the start was an h on the denominator, and when I do the limit as h approaches 0, I want to make h be 0. Even though it's not a substitution, it doesn't equal 0, still it gets very close to 0 and I effectively substitute. I can't do it with an h denominator. But now this x minus x is going to cancel itself out, and I'm left with h over h, which will simplify to be the limit as h approaches 0 of 1 over square root of x plus h plus the square root of x. My h's have cancelled, and now I don't have an h factor on the denominator. I have an h here, but it's not a factor, so it's not a problem. What I can do now is lose my limit. The limit as h approaches 0 of this expression is going to be, if I effectively make h 0, I'm going to have root x plus root x on my denominator. So I'm going to have 1 on root x plus root x, which is equal to 1 on 2 root x. Okay, now I want to point this out. I can rewrite this as a half times x. Root x on the denominator means x, the square root part gives me a power of a half. The fact that it's on the denominator makes it a negative power. So I've got a half x to the power of negative a half. Now remember that this is what I started with. F of x equals the square root of x, which can be rewritten as x to the power of a half. So what I've done is I've taken this half, I've multiplied it out the front, and I've subtracted 1 from the power. A half minus 1 gives me negative a half. Of course, I could have got there very quickly using the rule, but because I was asked to do this by first principles, I can't just take the shortcut. But it's good to point out that the rule still works. All right, now I'm going to do some worked examples following the rule. My first worked example is f of x equals 1 on root x. The first thing I want to do is rewrite this as x with a power, because if I'm going to be multiplying by the power and subtracting from the power, I want the power as a number rather than this square root symbol. So it's on the denominator, that means it's negative. It's a square root, that means it's a half. X to the power of negative a half. So f dash of x is going to be, I multiply by this negative a half, and then I'm going to keep my x, I'm going to subtract 1 from this power. Negative a half minus 1 gives me negative 3 over 2. And that's that example. All right. For the next one, I'm also going to have to do some simplifying before I can actually find the derivative of this. So I'm going to rewrite f of x into two separate fractions. This is 2x over root x plus 3x squared over root x. But the root x I can rewrite as a power of x. 2x over x to the power of a half plus 3x squared over x to the power of 1/2. Now I can simplify these just by using my index laws. I can subtract the powers and simplify each of those fractions separately. So 2x divided by x to the power of a half, if I subtract the powers, 1 minus a half gives me a half. And here, 3, it's x to the power of 2 minus a half, which is 3 over 2. Don't write 1.5. Write it as an entire fraction. Okay, I'm ready to differentiate now. So f dash of x then, if this is f of x, I take this power, I multiply it out the front, so I get 2 times 1/2 x, and now what happens to the power? 1/2 minus 1 gives me negative 1/2. And the second term is going to be 3 times 3 over 2. I'm going to run out of room, so I'll just write it as 9 over 2. X, 3 over 2 minus 1/2 gives me x to the power of 1/2. Now in this case, this is quite easy to rewrite using my square root symbols, and I was given a square root symbol in the question, so I'm going to do that. This is x, 1 over the square root of x. This 2 times a half cancels. X to the power of negative a half is 1 over the square root of x, plus 9 root x over 2. Now, I'll just revisit this one. I left this one in this form because it's negative 3 over 2. It doesn't feel to me any more straightforward to rewrite this. I could, negative 1/2, and this on the denominator I'm going to have the square root of x cubed. Okay, I could do that. Either way is fine. All right, my last example, if I look at it, is a composite function. I've got 1 over the square root of 2x squared minus 5x. So I've got the 2x squared minus 5x is the inside function, and then 1 over root x is the outside function. I'm going to define my inside function, let u equal 2x squared minus 5x, and I'm going to use the chain rule to solve this because it's a composite function. So I rewrite y in terms of u, and now I have to differentiate y with respect to u and u with respect to x. Now this one I've already done, so I'm actually just going to take the step of looking at the answer I got before. It was negative a half, right? This is the same. 1 over root x, negative a half, x to the power of negative 3 on 2. dy du equals negative 1/2 x to the power of negative 3 on 2. And you'll meet that one quite frequently. And du dx is 4x minus 5. I multiply that 2 by the coefficient out the front to get the 4. I subtract 1 from the power, so now it's not x squared, it's just x. And the 5x becomes just 5. Now to find dy dx, I'm going to multiply dy du times du dx. So dy du is negative 1/2 x to the power of negative 3 over 2, multiplied by du dx is 4x minus 5. Make sure to use your brackets, otherwise it's just multiplying by this first term and it's just minus 5 on the end, when in fact we want to multiply by this whole thing. Okay. I've made an error here. This should be a u and this should be a u. Alright, because I went to do my last step of substituting u and I realized I didn't have a u. Yeah, this needs to be a u because this is not dy dx, this is dy du. So now I substitute u, which is 2x squared minus 5x, negative 1/2 2x squared minus 5x to the power of negative 3 on 2 times 4x minus 5. There's nothing else to simplify there. I can't expand this bracket. Yeah, so I'm going to leave it as it is. And they're my worked examples. So that's it for differentiating rational powers.